everyone, welcome to part 3 of chapter 17. Today we're going to continue our talk with acid-base titrations, and we are now going to look at what happens when a weak acid is titrated with a strong base, or when a weak base is titrated with a strong acid. So instead of what we were doing last time with both the strong acid and the strong base, now one of our species is going to be weak. And so we're always going to start with our weak species, whether that's the weak acid or the weak base, and then we would titrate it with a strong species, so a strong base or a strong acid. So that is what we're going to cover today. All right, so let's look at what the titration curve looks like for a weak acid with a strong base. So here it is. So this one here, right, this is acetic acid, and so the top curve is the titration of a weak acid with a strong base, whereas the bottom curve is the titration of a strong acid with a strong base that we looked at last time. So if you'll notice, when we are titrating a weak acid with a strong base, there are a couple things that are different with this curve. The first of these is that the pH is not starting as low. Right? The pH now starts around 3. Anywhere between 2 and 4 will signal a weak acid, whereas something, 1 or below is typically going to be a strong acid. You'll notice there's this little characteristic kind of hump that happens here, and then it kind of flattens out. This is going to be what's called the buffer region, and we're going to talk more about that later. The other thing that's really characteristic of a weak acid being titrated with a strong base is that you'll notice the equivalence point has moved. When we did a strong acid with a strong base, the equivalence point was at 7 because it was a neutralization reaction and it resulted in water and a salt that had no acidic or basic properties. Well, now when we titrate this weak acid with a strong base, we're actually going to end up with the conjugate base after the reaction. So when we have a weak acid, we titrate it with a strong base, we produce water and this weak base. And so the weak base will actually undergo an equilibrium with water, making hydroxide ions in solution, which ends up dragging our pH a little bit over 7. So you'll notice when you have a weak acid that you're getting not as low of an initial pH, and again, that equivalence point has moved. Everything will be the same after the equivalence point because, again, we're going to have excess strong base in essentially water, so that calculation will end up being fairly similar. All right, so when we titrate a weak acid with a strong base, like I said, we're going to have a difference in the excess acid region, so that's going to be the stuff before the equivalence point, and then the equivalence point, like I said, has moved. It will now be a little bit higher. The way that we calculate the initial pH is going to be different now than when we were doing the strong acid because strong acids dissociate completely in water. When we are looking at a weak acid, right, the weak acid does not dissociate completely. It undergoes an equilibrium with water. And we know how to calculate the pH from that. We've been working on that for quite some time. So you'll need to use the Ka and figure out the concentration of the hydronium ion and then calculate the pH from there. The pH in the excess acid region. So this would be after you've started adding base, but you haven't reached the equivalence point yet. You would determine the pH there just like we were doing for buffers. Okay, and so that would be with the Henderson-Hasselbach equation. You would use your weak acid and your conjugate base concentrations in that equation. The pH at the equivalence point is a little bit tricky because we're going to need the Kb of the conjugate base of the weak acid. And so people often will think that this one is the trickiest or at least the longest calculation in the weak acid strong base curves. And then the pH after the equivalence point is we're just going to look at the excess strong base. There will be some conjugate base in there, right? Because all of our acid has completely reacted with base to produce our conjugate base, and then we added excess strong base on top of that. So we've got conjugate base and strong base in solution, but the basicity from the conjugate base is going to be negligible in the presence of a strong base because the strong base will contribute so many more hydroxide ions than that conjugate base will. All right, again, I keep trying to hit this home. when we have that weak acid with a strong base, two differences, right? The equivalence point not at 7, and we're going to have a buffer region exist as you approach the equivalence point. So that's what, when we were looking at the curve, that will be this area. That's where we can use the pH is going to equal the pKa plus the log of the base over the acid, okay? We can still calculate the volume of the base that we need to reach the equivalence point using that equation there, the MAVA equals MBVB. But again, make sure that you are using this only for things that react in a 1-to-1 ratio. Otherwise, you're going to need to do that through dimensional analysis and stoichiometry. The reason that we can use this equation, though, if they react in a 1-to-1 ratio for these weak acids, is because weak acids require just the same amount of base as the strong acids do, because they dissociate as they are neutralized. So we still have the same number of acidic hydrogens that need to be pulled off by that strong base. They just aren't free in solution yet. They're still kind of attached to the molecule. All right. So a bunch of different calculations that are going to be going on here. At the beginning, right, in this initial solution, this is just a weak acid problem. You're going to do this just like we would any other weak acid equilibrium. You're going to write the equation for your acid reacting with water to produce hydronium ion and that conjugate base. You'll go through all the Ka calculations, figure out your concentration of hydronium ion, and use that to calculate pH. In the buffer region, this will be once you've started adding base, but you haven't reached the equivalence point yet. Some of your acid will be converted to conjugate base, so in solution you will have both weak acid and conjugate base. Therefore, you have a buffer. So you can use the Henderson-Hasselbach equation in that area, which will simplify your calculations a lot. Halfway to the equivalence point, the pH will be equal to the pKa. And that's because if you think about our equation, our pH equals pKa plus log of the base over the acid, right? At halfway to the equivalence point, that means that half of our weak acid molecules have been converted to conjugate base. So we will have exactly equal concentrations of weak acid and conjugate base because half of it remains as weak acid and the other half has been converted to conjugate base. So when these concentrations are equal, this whole thing, right, we're taking the log of 1 essentially, and the log of 1 is 0. So at halfway to the equivalence point, the pH will be equal to the pKa. This can be really useful because you can actually go through and figure out the Ka of your acid and identify it if you needed to. So that's really useful. You need to know how to do the equivalence point calculation here. We're going to go through an example of that because it's a little bit interesting when you first go through it. And then after the equivalence point, your pH will depend on the excess base that you've added. This is going to be just the same as we did with the strong acid, strong base calculations. You'll figure out how much extra hydroxide you've added, divide that by the total new volume, figure out your concentration of hydroxide, and determine the pH from there. All right, lots of example calculations today. So before the equivalence point, like I said, that initial pH is going to be the same as the pH of the weak acid solution, just like we were doing for all of our equilibrium problems in chapter 16. And then after you've started adding base, but before you get to the equivalence point, you're going to have a buffer. So you're going to use the Henderson-Hasselbach and an ice table and all that good stuff. And again, like I said, halfway to the equivalence point, pH will be equal to pKa because you have a perfect buffer with equal amounts of your weak acid and your conjugate base. All right, let's start going through some problems. So here's one. What is the pH of 25 milliliters of 1 molar acetic acid before any sodium hydroxide has been added? And so we've got the Ka there. So again, before any sodium hydroxide has been added, we just have our weak acid. So the way that we are going to calculate this is through an equilibrium with water. Okay, so we're going to do an equilibrium ice table to find the pH of our weak acid. Okay, so since we are doing an equilibrium ice table, we are going to use the molarity of our acetic acid. Remember, equilibrium ice tables, we use molarity. Reaction ice tables, we use moles. So here we are, our weak acid, our acetic acid is going to react with water to produce conjugate base and the hydronium ion. So we'll make our ice table. So initially we have our 1 molar acetic acid, we don't care about water, and we have none of the other ones. And then we'll do our minus X and plus X, and then we'll have, add them straight down. Then we can put that into our Ka expression, and then we see that Ka is very, very small, right? We have times 10 to the minus 5, so we can use the approximation here. Typically in this chapter, I won't ask you to check to make sure that it's valid. I'm just going to allow you to use this approximation because all of these weak acids are not going to dissociate very much. So we're just going to go ahead and assume that in these titrations, our assumption is valid. So we'll use this approximation here, get rid of that minus X on the bottom because the change in our initial concentration is going to be negligible. And then we'll go through and we will solve for X. And remember, X is the concentration of the hydronium ion. So now we can plug that in, we can take the negative log of that and find the pH. If you'll notice, our initial pH is not very low, right? It's still acidic, but it's not super acidic. This is very characteristic of a weak acid. Weak acids tend to have an initial pH anywhere between 2 and 3.5 or so. All right. What is the pH of the solution after 10 milliliters of 0.15 molar sodium hydroxide has been added to 25 milliliters of 0.1 molar acetic acid? All right, so now we have started adding our base. So once we've started adding our base, now we have an acid-base reaction. So your first thing that you should always do is figure out how many moles of each one have been added and throw that into a reaction ice table. So let's start there. So we'll go ahead and we will calculate our moles of acetic acid. And so there we are. Now remember, acetic acid is a weak acid. It does not dissociate. It remains as acetic acid. And now we have our sodium hydroxide. We'll figure out how many moles of that, but sodium hydroxide will exist as hydroxide. So now we'll do our reaction ice table, again, in moles. And since they react on a 1-to-1 ratio, we don't need to go through and figure out the limiting reagent. We'll just use whichever one is smaller as our X value. So here, hydroxide is smaller, so we'll go ahead and we'll subtract our hydroxide amount from each one and add it to our conjugate base. Then we can add all of them straight down. And if you'll notice, we have weak acid and conjugate base left in solution. So when we have weak acid and conjugate base, that should tell you this is a buffer, okay? And so since this is a buffer, we can go ahead and we can use that Henderson-Hasselbach equation. We'll use this as our acid and this as our base. In order to use the Henderson-Hasselbach equation, we need to have the pKa. Right now we were given the Ka, so if we take the negative log of our Ka, that will give us our pKa. And then we can go ahead and put it into our equation, again with our acetate on the top and our acetic acid on the bottom. I'm going to stop here and talk about this for a moment because you'll notice that I directly used the moles from our reaction ice table in our Henderson-Hasselbach equation. And you should be like, whoa, hang on. You said that you have to do that in concentration. These are brackets. Those are concentrations. You're right. It should be concentrations. However, if we went through and we calculated the concentrations for each one of these, the way that we would do that is we would divide by the total volume, right? In each of these cases, we would divide by the total volume. Well, if you divide both of them by the total volume, those volumes will end up canceling out because they're in a ratio. And so we would actually end up being left with this mole ratio anyways. So I go ahead and, skip a step and don't calculate the molarities because, again, those two volumes, if we divide by liters on the top and divide by liters on the bottom, they will end up canceling each other out. So I take my moles and I put them directly in there. Please be careful with this. You can only do this if they are in the same volume. If you ever have a scenario where they are in different volumes, then you can't do this and you will need to go through and calculate the molarity. All right, so now we can go ahead, add those together, and we can get our answer here. You'll notice that it is slightly more basic than our pKa because we have slightly more weak base than we do weak acid. All right, let's go ahead and look at the equivalence point. So at the equivalence point, all of the weak acid has been neutralized and turned into conjugate base. Okay, so all of our acetic acid is now sodium acetate. So this is different from when we were doing the strong acid, strong base titrations, because in those scenarios, the strong acid and the strong base completely neutralized each other, and the salts didn't have any acidic or basic properties. Well, that's not true anymore. Now our salt, right, we would make sodium acetate. Our salt has acetate in it, and acetate is a weak base because it is the conjugate base of a weak acid. So our pH at the equivalence point is no longer going to be equal to 7 because one of the components of the salt has acidic or basic properties. Okay, so when we are left in solution at the equivalence point, we will have just weak base in water. Okay. When we go through and calculate this, I'm going to show you how to kind of calculate it the long way, but the short way is that if we know our original moles of our weak acid, all of those moles of weak acid have now been converted into moles of conjugate base. So you don't have to do this initial ice table that I'm going to show you. This is more going to be the proof that this is how it plays out. But if you know your initial moles of your weak acid, you can use that as your moles of your conjugate base. And then you will need to calculate the new molarity. So be really, really careful. It's easy for people to take the molarity of their weak acid and use that as the molarity of the conjugate base, but that's not what happens because there has been, more volume added to it. You've added all of that volume from the sodium hydroxide. So the number of moles of weak acid and conjugate base will be the same, but the molarity will be different because the volume has changed. So make sure to be really, really careful there. So you'll take your moles of your weak base divided by your total liters, and then you will do a weak base equilibrium problem just like you did in chapter 16. Most times at the equivalence point, you started with an acid and you ended up with a weak base, or vice versa. But the point is that you started with Ka for this weak acid, and for this you will need Kb, so just be careful there. You'll need to convert from Ka to Kb using Kw. All right, let's go through one of these. So first we're going to figure out what volume we need to get to the equivalence point, and then we'll go through and figure out the pH at the equivalence point. So this problem says calculate the amount of 0.15 molar sodium hydroxide solution that needs to be added to 25 milliliters of 0.1 molar acetic acid to reach the equivalence point. Since they are reacting in a 1-to-1 ratio, we can go ahead and use that MAVA equals MBVB, but I'm going to show you it through stoichiometry and dimensional analysis first. So we'll start with our liters of acetic acid. We'll use our molarity to convert from liters of acetic acid to moles of acetic acid. And then we'll use the mole ratio from the balanced chemical equation to convert from moles of acetic acid to moles of sodium hydroxide. So again, that step is going to use these numbers here. And then we can use the molarity of our sodium hydroxide to figure out the volume of our sodium hydroxide. And the reason that you might want to use this method is if things don't react on a 1-to-1 ratio. Here, since they do, we could have used this MAVA equals MBVB. We'll go ahead and rearrange. We'll solve for the volume of base, and then we'll have the molarity of our acid and the volume of our acid over the molarity of our base, and we can calculate our volume. All right, so now let's go through and figure out the pH of the solution at the equivalence point, right? We'll take that volume. I drug out a couple more significant figures here so that we can be a little more accurate with our answer, but I want to figure out the pH at the equivalence point is essentially how this plays out. So the first thing we want to do is we want to calculate the moles of everything that's been added, right? This is still an acid-base reaction, so we need to figure out how many moles of each one have been added. So there's our moles of acetic acid that we've had previously, and now we have our moles of sodium hydroxide. So when you see moles of our acid are equal to moles of our base, whether this is a whether this is a strong acid, strong base, or a weak acid, strong base, or a weak base, strong acid, whenever you have moles of acid equal to moles of base, that is always at the equivalence point. Okay, so we can go ahead and we can plug this in here. This is just to prove to you that this really does end up all converting into weak base. So we have our weak acid and sodium hydroxide, and then we'll subtract, the smaller one, but they're both the same, so we'll just subtract it there. That will leave us with no weak acid, no sodium hydroxide, and all conjugate base. So again, like I was saying earlier, if you know your moles of weak acid to start, that will be the moles of your conjugate base that you will end with after the reaction happens. And then you can use that to calculate the molarity by adding together the volumes. Okay. So again, after the reaction, we have only weak base, so now we're going to do a weak base equilibrium problem. So we will take our moles of base and we will convert it into molarity because we have to have molarity for our equilibrium ice tables. So we'll divide by the total volume to get our molarity of our conjugate base. Then we can go ahead and we can put it in an ice table and calculate that just like you would any other ice table. And then we will put this into a Kb expression. So note that now we are producing hydroxide, right? Because acetate is acting as a weak base. However, we were given Ka, so we need to go ahead and find Kb. So Kb will equal Kw over Ka, and we can go ahead and solve that. And then we can write our Kb expression, which will be our acetic acid times our hydroxide over acetate. And again, I'm going to go ahead and say that we can always use this approximation. This is times 10 to the minus 10, so this is very, very small anyways. And then we can go through and solve for x. And when we solve for x here, remember that this is the concentration of hydroxide. So when we take the negative log of that, we are getting POH, not pH. But we can use our POH to go ahead and find the pH because we can just do 14 minus that value to find our pH. So just to hit this home, why is the equivalent higher than 7, right? Why is that again? Because we are producing weak base in solution. We're starting with our weak acid, and once we add a bunch of hydroxide, we are converting all of that into weak base. Okay, it's very different from our strong acid, strong base solutions where those salts didn't have acidic or basic properties. These do, so you need to figure out, is the salt that I'm left with going to act as an acid or a base? In this case, since we have, weak acid, we will be producing conjugate base, which will, when that conjugate base reacts with water, it will produce hydroxide ions in solution, and that pH will be greater than 7. After the equivalence point, our hydroxide is in excess, right? We've just added in more hydroxide past the equivalence point. And this calculation will be very similar to the calculation we've done previously because we are not going to take the weak base into account when we're calculating the pH after the equivalence point because that weak base is not ionizing very many water molecules. Remember, the last one had times 10 to the minus 10. It's not producing very many hydroxide ions in solution, whereas the strong base is going to have a lot of hydroxide ions in solution. So we're just going to determine the number of excess moles of hydroxide, not total moles of hydroxide, but excess moles of hydroxide using a reaction ice table, just like we did previously. And then we'll find that molarity, we'll find the POH, and then convert it to pH. So here's an example. This says, what is the pH of the solution after 20 milliliters of 0.15 molar sodium hydroxide has been added to 25 milliliters of 0.1 molar acetic acid? So again, this is an acid-base reaction. We're adding strong base to our weak acid. So the first thing we want to do is go ahead and calculate the number of moles from each one. Our moles of our acetic acid haven't changed, but now we have more moles of our sodium hydroxide. So when we put this in our ice table, we'll notice, right, that now we have more moles of our strong base. So when we do our subtracting, when we subtract the smaller one, we're now subtracting our moles of our weak acid. And when we add everything up, we are going to be left with strong base and weak base. This is not a buffer, right? We are left with two things, but this is not a buffer. So we have strong base and we have weak base. we are going to completely ignore the weak base because the contribution to the hydroxide ion concentration is going to be totally negligible in the presence of this strong base. So we're going to use this excess moles of strong base to calculate our pH. So we have our moles divided by, again, our total volume. We'll get our molarity of our hydroxide ion, and then we can calculate the pOH and then convert that to pH. Again, whenever you're doing anything with hydroxide, make sure that you're calculating pOH and not pH, and just double check that your answer makes sense, right? If we have a bunch of excess strong base, it should be a very basic pH. So that's how you do weak acid, strong base titration curves. You can also do weak base, strong acid, which is essentially exactly the opposite. Okay, now we are going to start high and end low, just like when we talked about strong base being titrated with a strong acid. These are going to be different than the strong base versus strong acid. When we have weak base, our base will not start as basic, right? This is a pH closer to 11 or so, anywhere between like 10 and maybe 12.5 is going to be a weak base. And then our equivalence point will be below 7. And the reason the equivalence point is going to be below 7 is because all of our weak base will be converted into conjugate acid. And so when we have a bunch of conjugate acid, right, it's producing hydronium ions, which will make our pH acidic. Okay, so our pH for these curves is going to be less than 7. We still have the halfway to the equivalence point where the pH will be equal to the pKa. Just remember, it's always going to be equal to pKa. And so if you're given Kb, you'd need to calculate Ka and then pKa in order to be able to do that. So we also can titrate polyprotic acids, and we are actually going to do this in one of our upcoming labs. We are going to titrate a diprotic acid. And a diprotic acid would have 2 ionizable protons. Polyprotic just maybe says it has 2 or maybe 3, like in phosphoric acid. But in any polyprotic acid, whether it has 2 or 3 ionizable hydrogens, they will dissociate in steps. Okay, and so we won't just have one equivalence point, we will have 2 or maybe 3 equivalence points. Each one of those ionizable protons gets their own equivalence point. They get their own inflection point in the curve. And usually these Ka values will be very, very, very different, and you'll see very distinct curves. If they were really close to each other, you might not see really good separation between those Ka values and not great equivalence points. Typically, though, you'll see very large differences in the Ka values, and so we'll get this characteristic curve. So this would be a diprotic acid because we have 1, 2 equivalence points. Okay, and that's pretty much the extent of what we are going to do with this titration of a polyprotic acid for lecture. We will talk more about how to do these calculations for the diprotic acids when we get to that lab. For each one of these titrations, there's going to be a buffer region right here and right here. And then we will have the excess base region, just like we did before. We'd have the initial initial calculation of pH, just like we do. The only difference here is that we will have 2 equivalence points instead of 1. Okay, so when we are trying to figure out, the equivalence point, or, just monitoring the pH in general, a lot of times we will use a probe to measure the conductivity of the solution because of the hydronium ion concentration. And we have these really specific probes, and they just measure the concentration of the hydronium ion and then convert that to pH. And so it's really cool. If you are doing like a strong acid, strong base titration, the pH should be 7. You can actually put this probe in your solution, right, like in your Erlenmeyer flask, while you're doing your titration, and it will collect data and generate these pH curves, which is really cool. And so we will be generating these pH curves in our titration of a diprotic acid lab, and we'll be using that to identify the diprotic acid. So it's really neat. but we don't often use these probes during the titrations because we don't need them to be that specific typically. Most times we will use an indicator when we're doing a titration, but it's just important to use the right indicator. Thus far, we've pretty much always used phenolphthalein for everything, and so it's a common mistake to think that we just use phenolphthalein for all things, but we don't. We will use a variety of different indicators based on the pH of the solution that we are looking at. So we're going to look at how to choose an indicator, which is kind of fun. But I want to make sure that we all recognize the end point of the titration is when the indicator changes colors. The equivalence point of the titration is when our moles of acid are equal to our moles of base. We want our equivalence point and our end point to be the same or as close to the same as humanly possible. Okay, so it's really important to pick a good indicator. So you're going to want the pKa of the indicator to equal the pH of your equivalence point so that you get the color change happening exactly when your moles of acid are equal to your moles of base. That would be ideal. So here's what it looks like when you monitor your pH with a pH probe. You've got your little probe here, right? And this is our unknown hydrochloric acid solution. And then we're adding sodium hydroxide. So you can see our equivalence point is here at 7, right? But you can use that to generate this pH curve, which is really cool. Most times though, like I said, we are going to use an indicator. And indicators are dyes that just change color depending on the pH of the solution. These dyes are usually weak acids, and they will establish an equilibrium in water and between the water and the hydronium ion concentration, which is why they're really good for monitoring or for measuring pH. When the concentrations of our indicators are approximately 1, then we'll get a mix of colors, but typically that's not really common. Usually we will see a color when it's acidic and a color when it's basic, and we will use that to see when this proton comes off of the indicator. And again, we want our indicator to have the pKa similar to the pH of our equivalence point. So again, indicators are used to signal the end point of the titration, not the equivalence point, and they usually have a pretty small interval of pH over which they change colors, and it's going to be about 1 pH from the pKa of the indicator. So let's say the pKa of the indicator is 6, well then they would change color somewhere between 5 and 7. And that sounds like a really wide range, but if you think about our titration curves, right, like if our titration curves looks like this, our pH range, like from 5 to 7, would be here. And that's not a very large difference in our volume. Okay, so the fact that it changes over plus or minus 1 pH point from the pKa is actually totally fine. You're still going to see a very sharp change in color. Again, we want it close, the color change to be close to the equivalence point, which means that we want the pKa of the indicator to match the pH of the equivalence point. So here's phenolphthalein. We're all very familiar with phenolphthalein at this point. It's clear in acidic solutions. It's really pretty dark pink in basic solutions. And we're usually aiming for that really faint pink where you're holding it up to a piece of white paper and you're like, is it pink? I don't know. Let me ask someone, right? That's what your goal is. And if you'll look, the color change happens somewhere in here, right? So it looks like phenolphthalein changes color around 8. So we can use this for strong acid, strong base titrations that change pH at 7, but maybe that's not the best indicator for it. However, if you have a weak base and a weak acid and a strong base, that means that all of the weak acid at the equivalence point will be converted to weak base, which means that the pH will be slightly above 7. So phenolphthalein is really good for a weak acid, I'll write it down, weak acid, strong base titration. Okay, because again, at the equivalence point, all of that weak acid will be converted into conjugate base, which makes our pH slightly higher at the equivalence point. So really good for that. Methyl red is a different kind of indicator. It's kind of a pinkish red in acidic solution, and it's a yellow or like a yellow-orange in a basic solution. And it will change color closer to like 5 or 6. So again, it wouldn't be ideal for a strong acid, strong base solution because it doesn't change color at 7. It changes color slightly below it. This would be really good for a weak base, strong acid titration because at the equivalence point, all of the weak base has been converted into conjugate acid, which means that the pH at the equivalence point will be more acidic than 7, so it will be lower than 7. So this would be a good indicator for that kind of titration. So again, when we're monitoring with an indicator, we have a very large change in pH for a really small addition of titrant near the equivalence point. Even just like a drop or two of additional base or acid will cause this huge jump in pH. So even though they change color over, maybe 2 or 3 pH points, that's okay because we're still going to see a very sharp change in color. But again, we want the pKa of the indicator to equal the pH at the equivalence point. So here's one. Here's some different ones. Say we had 2 indicators lying around the lab, and we were going to do a weak acid, strong base titration. We know it's a weak acid because it's starting around 3, and that equivalence point is ending up above 7. So if you look, methyl red would be a terrible indicator for this reaction. It's changing color around 6. That is nowhere near the equivalence point, and we would not, our end point and our equivalence point would not be the same. Thymol blue, though, would be a decent indicator because it's changing color right around the equivalence point. It's going from yellow to blue right around the pH of the equivalence point. So that would be pretty good. Neither one of these would be very good for a strong acid, strong base titration because methyl red would change color before 7 and thymol blue would change color after 7. Neither one would change color at 7, so you would want to pick a different one if you were doing this type of titration. So again, you're looking for the color change to be happening right when your equivalence point is happening, right? You want your end point and your equivalence point to be the same. So here's a bunch of different indicators, right? Again, you're going to want one that's changing color at the pH that you need. And so there's tons of indicators. So you would just pick whichever one suits your reaction and go from there. So we can actually be really fairly specific with our indicator choice, and we can get fairly good endpoints that match our equivalence points if we're smart about which indicator we choose. And this is the end of this set of slides. We have talked today about weak acid, strong base titrations. We have talked about weak base, strong acid titrations really briefly, but you do them the exact same way. They're just going to, instead you're going to start with weak base and be adding acid. We then talked a little bit about monitoring pH with pH probes, which, like I said, I think is really cool because you can generate a pH curve and you can use that to identify unknown acids. We also talked a lot about choosing indicators and how the indicator will change colors over a specific pH range. This particular section is challenging for a lot of people because they often get tripped up on, where in this titration is, where in the titration is this particular calculation happening. My recommendation to you is, it's always going to be an acid-base reaction, or it's going to be just weak acid, or just weak base, or just strong acid, or just strong base if you're at the beginning of the titration. But if you're anywhere that's not at the beginning of the titration, it is always going to be an acid-base reaction. Your first step should always be to calculate moles of each thing and throw it into a reaction ice table. And then do your reaction ice table and then see what's left. And that will tell you how to calculate the pH. If you have weak acid and conjugate base, it's a buffer. If you have excess strong acid, there you go, calculate the pH from there. If you've got excess strong base, calculate the pH from there. But the first couple steps of these problems are always going to be the same. The more problems you do of these, the better off you will be, and the more it will make sense because you'll see all of the types of problems again and again and again. So make sure you're getting all of the practice you need to feel confident with these problems moving forward. As always, if you have any questions, please send them my way and I am happy to help. I like talking about acid-base reactions. I think they're really fun because they're super math heavy, which is kind of my jam. So if you need help, please send any questions my way and I'll be happy to help you out. Otherwise, keep getting lots of practice doing the problems on the lecture worksheet, and I will talk to you guys next time.